Hey, Jack, thank you for coming in today to do this interview. What a background. I mean, you are really the foundation for anything to do with high performance computing and incredibly massive adoption around the world. You're the standard. Everybody uses your libraries. If they want to do anything in terms of scientific computing, with this sort of mathematical element to it, that's you. And of course, you've built communities around that. You've been a mentor to students. And a lot of people, because my audience are also CEOs and investors, they don't realize that when they do high performance computing through some of their labs or they see it being done, especially with things like pharmaceutical sciences or in simulations, that's your work. If it wasn't for your work, it wouldn't be possible. So, and congratulations on achieving the ACM Turing Award, which is really the epitome of contribution in computing science. So again, thank you.
Well, Stephen, it's nice to be here with you today. My head is still spinning from the announcement. I have to say, it came as a total shock, and I have tremendous respect, and I'm humbled by by being given this award. I have known about the Turing Award. I've worked with some of the people who have received the Turing Award. Some of them are my mentors. This is, the people who have received it are really pillars in the computer science community. I've studied from their books. I've used their theorems. I've interacted with them on research papers, and to be in a position to now receive this award is really something I had never dreamed or had never really imagined would happen, and I'm completely blown away by the honor. I only hope that I can live up to the greatness that the recipients of this award have shown, and I hope I can be a mentor to students in the area in computer science that follow.
Well, definitely you'll be a guiding light for the world. And just to provide a bit of context, because I work with CEOs and investors a lot, we do a lot of data analysis and things like that. And really the foundation of all of that is your work. And the other thing too is that we do sort of an analysis of the number of PhDs out there. We estimate there's probably 16 million PhDs out there. So you're like in the handful of people who have this award. So really, it's just an amazing, distinguished honor. My audience is always curious, and that is, what are some of the inflection points that created this marvelous career, Jack? I mean, maybe there's two or three. It could have been when you were very young, maybe some people mentored you. Can you think of any things that really made you who you are today, and you're still continuing to contribute?
Not quite dead yet. That's right. So let's see. I guess I have to go back to when I was an undergraduate. I wanted to actually had aspirations of being a high school teacher, and I grew up in Chicago. And there's a place where many of the high school teachers were educated in Chicago. It was at one time called the Normal School, and I think today it has the name Chicago State University. That's the name that it had when I finished there. And in my time there as an undergraduate, I took math and science courses, and I did pretty well in those courses. I was probably a mediocre student in many of the other courses. But I did excel in math and in physics and chemistry. And my physics teacher, actually in my last year as an undergraduate, he suggested I apply for a position at Argonne National Laboratory. So Argonne is a Department of Energy laboratory. It's located outside of Chicago. And it was in my last semester. I would get credit by working with the scientists, basically, was the program. So I went off and did that, and that was transformational. I had a terrific experience there. I had clearly a love for the work that I was given to do. Now, as an undergraduate, I wasn't given lot of serious work, but I was given enough work that I could see that what was there was going to be fun, it was going to be interesting, and I could find a way to make a contribution to it. So I did that, and in my last semester, I quickly applied for a master's degree at the Illinois Institute of Technology, and I was accepted. I think they had a cancellation or something, and I was accepted. So I finished my undergraduate career at Chicago State University, decided not to go into become a high school teacher, but to look at computer science, and did a master's degree at IIT. And while I was at IIT getting this master's degree, Argonne National Lab said that I could work 1 day a week. So they basically hired me for 1 day a week. I was taking classes in Chicago at IIT. And after about 1.5 years, I got my master's degree. And then Argonne said, why don't you work here full time? So I went into a full-time position with a master's degree at Argonne National Lab, and worked on the development of some software libraries, mathematical libraries, which are really fundamental and ubiquitous in terms of their fitting into different applications. So the package I was working on was called IcePack, and it stands for Eigenvalue Package. So it's computing the eigenvalues and eigenvectors of a matrix, linear algebra computations, which again are really core to many computations. After that came a project called Linpack. I was the person at Argonne responsible for Linpack. It had collaborators from a number of places: the University of New Mexico, University of Maryland, and University of California, San Diego. And the 4 of us got together every summer at Argonne and worked on this package called Linpack. Again, I had a master's degree. The colleagues that were coming in and working with me sort of encouraged me to go back to school and get a PhD. And I decided that that was the right thing to do for a number of reasons. One reason being it was my let me call it union card. It's my calling card. So without a PhD, certain doors wouldn't be open. Perhaps with it, I would be able to do things. And I went to the University of New Mexico and worked with one of the colleagues on Linpack, a guy called Cleve Moeller. Cleve was a professor in the math department at the University of New Mexico in Albuquerque, and I went off and did my coursework with him. I arranged to work at Los Alamos, again, spending 1 day a week at Los Alamos, working with the people there who were running on one of the first vector supercomputers, a Cray 1. And that was, again, a transformational time for me, learning about high performance computing at a very close level. The machine, the Cray 1, was just being installed and put in place there, and I got to get my hands dirty, so to speak, on developing software and writing algorithms for that machine. So that was a great experience. Then after getting the PhD, I went back to Argonne National Laboratory and continued working in linear algebra. So there were many things that sort of led up to it. I'll say the first thing was this really inflection point where I decided to go into computing, got the opportunity at Argonne National Laboratory, worked there for a short period of time, and really loved the work overall.
Just a remarkable journey, and it's really interesting how you got into this really applied area with linear algebra, and it's sort of the foundation of everything you do. And even with Linpack, that in the top 500 list of which you're sort of foundational too. But I can see you then, you're now the University Distinguished Professor of Computing Science at University of Tennessee. You're distinguished research staff in computing science and so on at Oak Ridge National Laboratories, Turing Fellow at Manchester University, adjunct professor at Rice University, and you're the director of this innovative computing laboratory, the University of Tennessee, and it's been a spawn for so many students and PhD students and so on. And I just want to take a few minutes and talk about that arc, your career arc as you're at the University of Tennessee in this innovative computing laboratory. And you've been such a great mentor. I mean, your students are everywhere, right? So.
Well, yeah. So let's see. Just to pick up on that story and move into the thread that you're alluding to, I was at Argonne National Laboratory basically from 1972 when I was an undergraduate until 1989. And in 1989, I decided I had an opportunity to come. A colleague proposed coming to work at the University of Tennessee and also Oak Ridge National Laboratory. So the University of Tennessee is located in Knoxville. Oak Ridge National Lab is in Oak Ridge. It's about 40 miles apart, and it was going to be a joint position. And I knew how the Department of Energy laboratories worked, so that was a comfortable fit. And I felt it was time that I go into an academic setting. And I didn't have any, real experience. At one point I wanted to be a high school teacher, and I thought maybe it would be great to try my hand at a university professorship. So I was given that opportunity. I had a joint position at the University of Tennessee and Oak Ridge National Lab. I started with one person. I hired one person to help with that at the University of Tennessee. And then over the next 32 years, I guess I've been here, I've built up a group, and the group is called the Innovative Computing Laboratory. We're located in the Electrical Engineering and Computer Science Department at the University of Tennessee and the College of Engineering. And we have a group now that has grown to about 45 people. And that group is composed of research professors, postdocs, graduate students, undergraduate students. We have an administrative staff that keeps everything working and moving along. So I operate sort of like a department at many levels. We have research money. Everybody's on soft money in this context. Soft money is where we write grants and proposals and get funded to do some research. We have a portfolio probably of 20 different grants, many from the Department of Energy, some from the National Science Foundation, and other organizations as well. So we have research projects. Those projects are typically 3 to 5 years in duration, and then we write proposals, and sometimes we fail, sometimes we're successful. We've been in a fortunate situation that our work has fit into many of the opportunities that are proposed by funding agencies, and we have done pretty well in terms of acquiring research funding that allow us to push our ideas forward and to experiment and to develop and to provide software and packages and algorithms that work for high performance computing. I like to think that we do three basic things here in ICL. We do work on developing algorithms and software for linear algebra. That's what I've been trained in. That's my core thing. We also put together different parallel programming mechanisms. And by that, I mean, all machines today are parallel. We need some way to express that parallelism at the programming level to allow users to match to the hardware that's there. And we've been instrumental in putting together tools that help. Sometimes those tools are put together by a community, not just my group, but an international community. So one of the tools that we put together is called, it goes by the name of MPI, the Message Passing Interface. It's the way in which we do scientific parallel computing today. I was instrumental in helping to put together that group of people that defined the standard. It's a de facto standard for doing parallel computing. And that's really the thing that's in place today. It forms, in some sense, the fabric on which we develop parallel programs for our scientific applications. And the third thing I'd like to say we do here is related to performance evaluation and benchmarking. So we've had some tools that have helped with measuring how capable some computers are. One of those tools is this thing called the top 500 list. So every 6 months, we put out a list of the 500 fastest computers, and that list is ranked based on a benchmark. that benchmark is called the Linpack benchmark, and that's something that has its origins back in the 70s, and that benchmark is used to rank these computers. And the idea is somebody implements the algorithm specified in the Linpack benchmark, solves a system of linear equations, and tries to implement that algorithm as best they can on their computer. We generate the matrix, we set up the problem, they have the mechanisms for solving that problem, and then we check to see that they get the correct results given the specification of numerical accuracy. And that's been going on for a long time. I think the top 500 list is probably 24 years old now. And again, it ranks the fastest computers, and we can track a number of things based on that. One of the things are trends in the area of large-scale scientific computing. So the top 500 list has a life of its own. It started many years ago and needs to be augmented with better tests, newer tests that reflect both the applications and the changing nature of the hardware that we have in place today. But it has served a purpose, a long-term purpose, and I think it'll carry on into the future as well.
There's just so much to unpack here. The funding for your lab and what you're doing, because you're so fundamental to the computer architectures out there and how that work's being done, then you must be getting grants from corporations as well, right? Or not?
So we do. We occasionally get awarded funding to help develop software and algorithms for the industrial setting, and we're happy to take those on. That's another aspect of the work that we do. We're intending to deploy state-of-the-art algorithms on machines that are state-of-the-art as well, trying to exploit them as much as possible in order to come up with very cost-effective, timely solutions to problems. High-performance computing, is the way in which science is done today. Simulation is at the core of many scientific discoveries today. And that simulation is done on high performance machines. And the government laboratories use them. They're also used in industry. It's interesting, we have this list of the top 500, and I was mentioning trends. One of the things that emerges in this list is that here we have the 500 fastest computers in existence today for scientific computing. And when you look at that list and look at where it's being used, where those computers are being used, what emerges is the fact that half of the machines on the list are being used in industry. So industry gets it. These computers, these high performance computers, are used to give an industry a competitive edge, and they're willing to invest in this scientific tool to help them in developing whatever products that they have. So it certainly goes beyond the what I'll call more of a scientific investigation. It goes to being very practical in terms of developing and furthering products that perhaps at a research side within the commercial areas. So there are many ways in which these machines are used. Scientific things are clearly a way. These machines are really, you should think of them as sophisticated scientific instruments, these supercomputers. And what I mean by that is, we have things like the Hubble telescope or the James Webb telescope now that's coming into operation. That's a sophisticated, complicated instrument which is going to be used to help astronomers push back the frontiers of science in their area, discover new things with greater fidelity, be able to go back and look at the origins of the universe and try to understand things that they really couldn't see before with the other kinds of instruments that they had. And these supercomputers are similar to that. We use these machines again to help with simulation, We use them to do things that we can't do or we can't recreate in a laboratory. So think of two galaxies colliding. You want to understand and study the dynamics of that. That's an experiment that we can't do in a laboratory. We have to do it through simulation on a supercomputer to really understand what happens when we push together these two galaxies and look at what the evolution will be for that system or for those systems. We use computers to help us in designing better products. So, an example is, the car companies, GM uses supercomputers to help design better, more safe vehicles. So, in the old days, they would take a model of a car and crash it into a wall. Today, they minimize that kind of experiment. What they do is they do modeling and simulation of those crashes on a supercomputer to try to understand what happens when when specific materials are put in place in a vehicle and looking at what happens in the collision. So they can carry out many experiments, tweaking the parameters to get something optimal that will be more cost effective, be better in terms of safety, and provide for a better overall vehicle for consumption. We think of that going on with the car itself, but also with seat belts and airbags and other things that are in these vehicles to try to improve the performance of them overall. So there are many ways in which high performance computers can help. Perhaps the way in which it touches us on a daily basis is when we see the weather forecast. So the weather is forecast or predicted or simulated on a supercomputer, and it's through that simulation that we understand what's going to happen in the short term for weather. And we use that same kind of device to help with climate modeling. So on a much longer scale, what happens if certain conditions are put in place? How will things evolve? What's the impact of things heating up and so on using high performance computers? So there's many ways of looking at it, many ways in which they can be used, and they really are very special purpose pieces of equipment, highly sophisticated to help drive science forward.
It's fascinating. I work with I guess over 100,000 CEOs and investors, and I really recommend they look at your lab and the work that's being done and really provide grants to your community to progress the work. And there's so many implications, including national security implications and so on as well, because I also work with national and international security folks and so on. So it's so pervasive in terms of its importance. I know that you're also part of the International Exascale software project, which is just fascinating, right? And this realization with this ultra high resolution data intensive methods, there's this whole requirement of replacement of HPC software. And that's because of these new designs that are coming out with this massive concurrency, different kinds of processors working together, and this idea of power budgets. And memory is changing. I mean, in my last discussion with John Hennessy, we talked about maybe, new advances in memory architecture and so on. So can you talk about some of that work, the exascale side, and then there's this competing sort of cloud side and where that's going? And do you think it's going to go to Zetta-scale, or do you think cloud's going to take over?
Yeah, so this is, so let me just touch on the first thing that you mentioned. The first thing is that you mentioned was the Exascale computing program. So the Exascale computing program is a program within the Department of Energy to put in place exascale based computing. So what's exascale? So exascale computing is looking at computers that operate at 10 to the 18 operations per second. So 10 to the 18, that's a billion operations per second. I have a hard time getting my hands around that number. So a billion computations per second is what this computer is capable of accomplishing. And the Department of Energy needs high performance computing to help drive its its scientific activities, its research program. The ECP program is going to put in place 3 exascale machines. I have a position at Oak Ridge National Laboratory. I was there last week, and they're standing up the first exascale machine in the U.S., and that's a machine called Frontier. It's a machine that will run at exascale, probably 2 exaflops is the way we say it. So 2 times 10 to the 18 floating point operations per second. These computers, each of these 3 computers has a price tag of roughly $600 million. So the Department of Energy is investing in $1.8 billion just in terms of the hardware. So think of that as the race car, right? So that's the component that's there to do the computations. In addition to that, well, not in addition, but what's required to use those 3 machines are a set of applications. So the Department of Energy has looked at and has identified some 21 applications that are intended to run on these exascale machines. So the Department of Energy has 2 components. One component is the open science laboratories. There are 3 major open science laboratories: Argonne National Lab in Chicago, Oak Ridge here in Tennessee, and also Lawrence Berkeley Lab out in the Bay Area. Those are the open science labs. And in addition, there are 3 laboratories which are used to help with the NNSA, the National Nuclear Strategic Administration. And those labs are thought of as helping with put in place helping with the testing for the nuclear stockpile. So those 3 machines, one's going to be at, those 3 laboratories are Los Alamos National Lab, Sandia National Lab in Albuquerque and in California, and also Lawrence Livermore Lab in California. So the DOE has 3 big computers, 21 major applications, and those applications deal with wind energy, nuclear energy, fossil fuels, combustion, magnetic fusion, chemistry, extreme materials, astrophysics, cosmology, earth science, and things like cancer research. And I'm sure I've left off a bunch of them. So those are 21 applications which have been identified, and people are working today to develop those applications so that they will run on those computers, those 3 computers. And in addition to that, there are 84 software projects. So software is, the thing that's going to fuel those applications and make sure that they run efficiently and effectively on those 3 race cars, if you will. So the software is being deployed and being built today for those 3 exascale computers. And that whole project, the applications and the software, the cost of that is roughly $1.8 billion as well. So the total cost roughly for the exascale computing project with the hardware, the applications, and the software is around $3.6 billion. And that's being done over a 7-year period of time. We're well into the 5th year of this project. So there's about 2 more years to go before the project completes. The hardware is just being stood up today. Frontier is, again, I saw the machine just last week. It's being put together and being put through its tests to make sure that it runs correctly. The other machine at Argonne is called Aurora, and then the machine at Lawrence Livermore is called El Capitan. And those computers will be deployed with various vendors and manufacturers involved. The Frontier computer at Oak Ridge is being put together by HPE. So that's the company that's developing the overall machine, together with AMD for the processors and Cray for the interconnect. So that's the composition of that computer. Very sophisticated piece of equipment, state of the art, being put in place to help drive the Department of Energy's mission needs.
There's just so many places we can go with this. I mean, I had a discussion with Humble, who runs the Quantum Initiative, at Oak Ridge, because I actually I chaired a session on quantum computing at Quantum Week. So, and I know that there's hybrid computing and sort of mixing quantum computing with supercomputing and so on. And a lot of the same problems with quantum computing, it's those very early, are the same problems that you're addressing with supercomputing. What do you think about quantum computing when it becomes more mature and you're able to get some stability and control of the noise, and you get, let's say, to 1 million qubits, stable qubits? What do you think about all of that? Because there's overlap, right?
Oh, absolutely. And you know, quantum is going to be an important tool that'll be used in helping computational scientists do their work. But just to put in perspective, you know, today our computers are composed of multi-core processors, and those multi-core processors are augmented with accelerators. And those accelerators, you know, that we use today are called GPUs, so graphical processing units are in place there to accelerate the rate at which we can do the computations. And the way to think of that is, you know, it's a hybrid system, multi-core. We have these GPUs, and over time, that collection or that ensemble of things is going to be augmented with other components. And one of the components I would see fitting into that ensemble is quantum computing. So I don't think quantum computing is going to replace the whole computer. I don't think we would throw away our exascale machines and put in place one quantum computer to carry out our computations. That quantum computer doesn't have the ability to do the kinds or the multifaceted computations that we need. When it does have very good capability for doing a certain kind of computation. So I would foresee a machine which had multi-core accelerators and quantum processors attached to it, so that those quantum processors could be used to augment and to enhance the rate of execution for certain aspects of this computation. And you know, we can think of extending that to specialized processors that help with machine learning or AI computations. And we might think of putting in place additional capabilities for neuromorphic computational components, things which react similar to the way our brain reacts to stimulations. So, you know, I think that there's a wide spectrum of capabilities here that will be deployed and used when they mature to the point where they can provide a significant advantage for certain kinds of computations, and they would be fitting into the spectrum of processing capabilities. You know, we think about optical computing. So think about, you know, using light to do the computation. That's another facet that could be put into place with these kind of computing devices over time. So, you know, I think it's wide open here where we go with this, and how that gets deployed is something that is going to be interesting to see how it unfolds in the future. So I would say there's, you know, great opportunity here for research, investigation, and development of devices for doing these kind of computations. You mentioned, you know, today we're at exaflops, so 10 to the 18, and the next threshold could be zettaflops. Okay, so another 3 orders of magnitude, 10 to the 21 computations per second. And you know, will we get to that point? Can we build a machine that has that kind of capability? You know, I'm questioning whether we would do that today. You know, we know that cloud computing is very attractive from a number of aspects within the area of scientific computing. We see cloud being deployed. Cloud has certain advantages. You know, I just talked about a computer that's going to cost $600 million, and that's a device that they're going to stand up and put in place, and it'll be used for, you know, maybe 4 or 5 years, and then it will be replaced with another computing device, higher quality or more computations. And you know, we think about maybe that's not the best way to do business. Maybe we can use the cloud. Maybe we can think about having resources that can be composed and put together and used and developed over time, so that I don't have to buy one piece of hardware and now I'm frozen in terms of using that piece of hardware. I can put together a cloud-based system which can be augmented with various components, and I could dial up essentially the kind of computing resources that I need to help in solving my computational problems. So I see great opportunities ahead. We see tremendous investment by companies like Google, Amazon, Facebook, to deploy these, Microsoft, to deploy these cloud-based systems. And we are seeing sort of a shift almost in terms of how things unfold. So we now have so today we take the way in which these computers are built is we take commodity off-the-shelf components, put them together in a box, a large box, and call that a supercomputer. So that's basically the way Frontier and Aurora and El Capitan will be put together, these 3 exascale machines, commodity processors assembled with a high-speed interconnect with a lot of memory, and that's going to be called our machine. And in the future, what we're seeing today with companies like Amazon and also Google is the ability for those companies to basically build their own hardware. So, Google has their own TPUs that they're using to deploy hardware for solving some of the challenging problems they have from the standpoint of machine learning. Amazon has a processor called the Graviton that they're putting in place, again, specialized for their own purposes. So they're not turning to Intel or AMD to buy chips. They're going to build their own chips. It's going to be built out of on top of things like ARM processors, the architecture from ARM, developing a processor which is tailor-made for their specific needs, and trying to leverage that in terms of helping to solve their problems in a more cost-effective way. So I see great things on the horizon for cloud-based computing as well. Those companies have a tremendous amount of funding that they could deploy. I think of it as being, they are exothermic in terms of the funding, the amount of money that they have, where companies, or not companies, but research groups like the Department of Energy is more endothermic, that they need funding to get them off and running, where the commercial side of the house is enjoying this growth today, and they're exploiting that growth by developing their own technologies that can help them even go further.
So just to my audience, and they know this because I do these interviews for a long time, we're actually at the, and they're unscripted, so we're at the end of the time period. I don't know, can you stretch a bit, or are you?
I think we go a few more minutes here, Stephen, that'd be fine.
Okay, so there's just so many different areas we can get into, but we just have a few more minutes. So I just want to get into your work with like HPCG, HPCAL, the AI machine learning. You're doing HPC simulations in the cloud and so on. What are your thoughts about that? There's so much work done now on large language models, for example, like transformer models. And supercomputing is really I could see as the basis for some of this as well, some of the massive kind of capabilities that you can do, right? So.
Okay, so you mentioned the benchmarks that we have. The Linpack benchmark is the thing we use to gauge the top 500. That benchmark was developed many years ago. So the basic benchmark itself, the concept that it's exploiting, that's implemented and run, is something that was put together back in the late 70s. And in the late 70s, computers had a certain characteristic. They were basically sequential computers, and they had floating point computations were very expensive on those computers. And the Linpack benchmark, the thing that we use for the top 500, is very good at stressing floating point operations. It's very good at measuring how fast you can do floating point. In fact, the computational kernel for that benchmark is matrix multiply, which is a very intensive matrix operation. It needs, so if I have a matrix of size n, I need n squared pieces of data. And in addition, I'm going to do n cubed floating point operations. So there's a surface to volume effect. The surface is the data, and the volume is the amount of computations you do on the data. And that highlights machines, it stresses machines where floating point is very expensive. So back in the 70s, that was the case. And as the computers have evolved, architecturally, they've changed in a number of ways. And one of the ways they've changed is to become, floating point has gotten very cheap on these computers. In fact, it's over provisioned on the computers. There's too much floating point capability is what I'm trying to say. And the thing that is a stress point now on these computers is data movement. So the floating point is not where the time-consuming part is. It's in moving data around inside the computer, on the chip itself, within the context of the memory associated with the chip, and then within the context of the neighboring processors, and then within the context of neighboring nodes. So we're connecting multiple millions of things together and interconnecting them with a high performance network. But that network is the strangle point, if you will. We've reached the memory wall on the chip itself. It's very expensive to move data around. It's one of the most expensive things that happens on a processor. And the benchmark that was good at doing the Linpack benchmark, matrix multiply, is not the good way to judge machines. So we've augmented that benchmark with newer benchmarks that perhaps reflect better in terms of the character of the work that's done on these computers. So within the DOE complex, we have these exascale machines that are being built. And the driving force for those exascale machines is really simulation. And what we're simulating is a three-dimensional problem. And when we simulate a three-dimensional problem, we have to discretize that problem. It's a partial differential equation that we want to solve. And that discretization leads to, again, a system of linear equations. But now the matrix is different. It's sparse. It's not dense. It's sparse. And we have different techniques that we use in solving that sparse matrix. And when we do that, we employ an iterative method, not a direct method, to solve that system of equations. And that leads to a different characterization in terms of the data movement and the floating point operations. And the problems that are solved on the DOE machines are more characteristic of that 3D simulation of partial differential equations and fit more with this HPCG benchmark that we have. And perhaps our dirty little secret is when we take a look at running the Linpack benchmark, something which is tuned to matrix multiply, we see roughly that we can get approximately 75% of the theoretical peak performance of the computer. So theoretical peak is sort of an artificial number. It's a number that we know we will never exceed. It's like on your car, you have a speedometer and it goes up to 160. And we know we're never going to be in a position of going to 160, we'll be much less. So the Linpack benchmark in that context gets 75% of its theoretical peak performance. That would be doing a reasonably good job of implementing that on a computer. The dirty little secret is that for doing these large scale simulations of partial differential equations on our computers, we're getting efficiencies which are probably measured in terms of 1 digit percent. That is to say, less than 10% efficiency. So this benchmark exposes, I'll say, some really serious potential issues with moving data around on these computers. And it's through that realization, I think, that we can perhaps develop better hardware, better architectures, better ways of expressing the problem so that it can, in the future, be a better match. So, we'd like to say there's this issue of co-design where the hardware people get together with the applications people, with the software people, and that we can co-design a piece of equipment that better solves the problem than if we were to just throw a piece of hardware over the fence and expect the applications people to figure out how to use that piece of hardware and then have the software guys do an implementation on that hardware. And today we're more in the camp of the hardware being thrown over the fence, and we need to be better into a position where we can help with this co-design and matching better the application with the hardware. And going back to the cloud example, that's where companies like Amazon and Google, I think, are doing a better job perhaps of matching their requirements to the hardware needs. And they can they have the resources, they're exothermic, they can invest in doing things at the hardware level that perhaps we can't do at the national laboratories.
Yeah, I mean, just one comment. I know TSMC is working on 3D architectures and RRAM, which has ultra high bandwidth on the chip. And then you looked at GTC and Jensen Huang and talking about the architectures played by, but that's another hour.
That's another talk. That's right.
So Jack, we're over time, and I know you got to rush to another meeting. Maybe one closing comment, and we'll close off this interview. So
sure.
So your final recommendations to the audience.
My final recommendation.
Yeah.
Okay, so what would I recommend? Well, to people starting out, find something that you're passionate about, go into it, and drive into it as much as you can, learn as much as you can about it. Expect to fail. You're not going to succeed at everything that you do. In my research, in my career, I fail often in terms of what I'm trying to do, and I learn from that failure and move on. Do things that you feel passionate about. My students, my PhD students here, when they come in and they're fresh, I give them a problem to work on, and they come back to me almost immediately and they say, I don't know how to do this problem. And I say, that's exactly the point. You are the person who has to investigate and figure out how to solve this problem. If it was easy to solve, I wouldn't give it to you. This is a research problem that you have to study and understand and try to grapple with. And hopefully they go away and learn something about that. High performance computing is going to be with us. It's a way to help us push back the frontiers of science. We're using it in more and more areas. It has a tremendous impact on the national economy and the competitiveness that we have. And we're going to produce better products and tools as a result of it. And there's a trickle-down effect, of course. Anything developed here for these high-performance computers has a trickle-down effect for many of the things that make their way into our common use, even like iPhones and cell phones and things like that. So I'll leave it there, Stephen.
Well, Jack, you're emeritus. Why'd you see you beginning? I really appreciate you coming in and sharing some of your insights with the audience. I mean, we could do a half a day. There's just so many areas to unpack. I really encourage the audience to take a look at the write-up that the ACM did when you won your Turing Award. And look at some of the articles of some of the work that you've done. I mean, it's so foundational. So again, thank you for your outstanding contributions, and they continue to accelerate. So thank you again.
It was my pleasure, Stephen.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.